Okay, let's get started. The next talk in the sponsor session will be by Burak about unlocking PostgreSQL's true performance with local SSDs. Thanks.
Hello, everyone. Today I'll talk about unlocking PostgreSQL true performance with local SSDs. My name is Burak Yucesoy. I work at UbiCloud. I am the lead engineer building UbiCloud's managed Postgres service. Before that, I used to work at Microsoft, and there I was leading the team building Azure Postgres for Azure Cosmos DB for Postgres. And before that, I was part of the Citus data team, which was a startup building a distributed Postgres. And before that, I was working on at SAP at the HANA team. So all my 4 gigs are about databases, and last 3 are specifically about Postgres and managed Postgres. It was kind of by coincidence at the beginning, but then it became a choice later on. And at UbiCloud, we are building a new cloud provider, and part of building a new cloud provider is building a managed Postgres service. And one cool thing about UbiCloud, it is completely open source. Everything is on GitHub. You can go check it out, play with it. If you have some servers, like on-prem or on a data center, you can deploy it and you would have your own cloud, basically. Or if you don't want to deal with any of that, you can use our managed services. You can just go to ubicloud.com and you can provision a managed Postgres database, Kubernetes cluster, like anything you would expect from a cloud provider. So back to today's topic. Today I'll talk about, today we'll explore different storage architectures, but with a particular focus on local NVMEs, like local storage versus remote storage. And right now, the industry heavily leans on network-attached storage or remote storage. And among those, especially if you look at the big, all 3 hyperscalers, their managed Postgres offerings are based on remote storage. But this particular trend isn't limited to managed offerings. I noticed that even people who have their own self-managed PostgreSQL, they still use remote storage. And I realized, well, obviously remote storage and local storage, they all have their pros and cons, but what I realized most of the time, people pick the storage architecture not because of the their actual use case, but just because it has been done in particular way, so they just continue to do it in that way. And the main claim that I want to do today is that, well, I think the local storage should be default. And today in this talk, I'll explain why I think that way. And to support my claim, I want to first share some benchmark numbers. Because the primary benefit of the local storage is its performance. When you use a remote storage, basically you are adding additional network hop. So every time you need to read data, if it is not in cache, or if any time you want to write data, all the data needs to go through a network hop to the remote storage. And this basically introduces a big performance penalty, which I'll show you in a minute, how that shows itself in benchmarks. So the first benchmark I want to share is pgbench. So pgbench is it's a building benchmark tool that comes with a PostgreSQL. So if you run any benchmarks with Postgres, you are probably familiar with this tool. And it is based on TPCB benchmark. And TPCB benchmark is a type of an OLTP benchmark. It is characterized by high concurrency and with small transactions. So I mean, let me actually show what TPCB benchmark looks like. So we just start a transaction. We just do a simple update. like it's just the update table set to this value where the ID is this, so like very simple update. We do a one select operation, another small update, one more update, we insert data, and we close the transaction. So there's nothing complex, very short queries, but we run lots of we run this transaction multiple times in high concurrency manner. And this is the TPCB benchmark. And when we run this benchmark on local NVMe versus remote storage, local NVMe actually is almost 6 times faster. It's able to run 6 times more transactions per second. There is another benchmark, it's called TPCC. This is a more modern version of TPCB. So actually, TPC Council, they depreciated the TPCB benchmark, and they replaced it with TPCC. But since PGBench comes with TPCB, this is like the most commonly used in Postgres ecosystem. But the more modern version of it is TPCC. And this is also, since it is like next version of the TPCB, it's also characterized by high concurrency and small transactions. And if you look at the example TPCC transaction, is that again we run a simple update, another simple update, we run a select, update, insert, and commit. So like, again, nothing complex, but the benchmark part comes from running this query many times. And again, when we compare this benchmark on remote storage versus local NVMe's, local NVMe's outperforms remote storage by 8.5x. Like these are same hardware, like same CPU, same memory. The only difference is one of them has remote storage, the other one is local NVMe. We talk about transactional workloads. Let's also look at an analytical benchmark, which is TPCH. This is also like another standard benchmark that is heavily used in our industry. And this benchmark emulates analytical workloads, which are mostly like very large scans, like you scan big portion of the data. So not much index lookups, but like you scan maybe half of the table, and you do complex joins. And TPC benchmark has 22 queries, and the benchmark, to run the benchmark, you basically run each query back to back, and you measure the total time. Or, well, according to spec, you actually get the geometric mean of all 22 queries. I'll show an example. This is a very simplified version of it, because actually TPCH queries are really long. So I had to cut some parts. But as you can see, we have like aggregation. We have like inline queries. We have like lots of tables, like 1, 2, 3, 4, 5, 6 tables joining with each other. We have lots of filters. We have group bys. We have like the ordering. So it is much more different than the transactional benchmarks we did. But the one thing is same is how local storage outperforms remote storage, which is, in this case, it's almost 8 times faster than in analytical workloads. And this is, like, you can think that these are like synthetic benchmarks. They might not represent the real workload, but we also have customers running their own actual databases, like their own actual applications on remote storage. And then after they migrate to UbiCloud with local NVMe's, they see like with the half specs, like the half memory, half CPU, they were able to get like the 3x better performance. So this is not just for synthetic workload. The penalty of going going over network is real, both for synthetic workloads and also the actual production applications. So that begs the question, like if local NVMe SSDs are really so much better, then why remote storage is used in like most of the PostgreSQL deployments out there? And well, I will talk about at the end, the remote storage has its own pros But what I realized is most of the reason is that it just happened to be. And I'll explain why this happened to be by having maybe a bit of historical background on storage technologies. So if you go way back, one of the oldest storage technologies was the tape drive. And the tape drive basically stores the data on this long magnetic strip that you can see here. And it would have a read head. And then whenever you want to read some data, these tapes would spin and would bring the part of the tape that you want to read or write right next to this head. And that means if you want to read a sequential data, it was quite fast. But if you want to do a random read, it was quite slow. So imagine that you are at the beginning of the tape and you need to read the data at the end of the tape. You need to spin the tape from beginning to end just to read the one page. And I like to think in analogies. So when I think about tape drives, it gives me that this is similar to linked list, maybe double linked list. So let's say you are at one particular node of the linked list and you want to go to another one. You need to go through every node one by one just to be able to reach to data. So that's why the random reads are quite bad, but sequential reads or reads or writes are good. And today, the primary use of tape drives is storing maybe a large amount of data in cold storage. We don't use this technology for databases anymore. But that said, when back then, databases were actually used with tape drives as well. One big difference is that those databases were mostly OLAP databases, or they used for batch processing. So they didn't need to do lots of random reads, so it was OK for them. So using Postgres with a tape drive would be quite unconventional, but I assume there were some old poor souls that had to use Postgres with tape drives, which would be quite bad experience. But I mean, at that time, you didn't have any other options. And more recent one, more recent technology, is HDDs. And HDDs are these are much more modern and similar to tape drives. They also store the data magnetically, but instead of a long strip, long tape we saw earlier, it stores the data on this spinning disks. And it would also have a read or write head that you can see here. So when you want to read or write a data to a particular location, first the disk would spin, and then the head would move to a particular lane on that disk to be able to access that data. And thinking about the analogies again, this is a bit more loose analogy, but if I still use the same data structure analogy, I think HDD is like trees, mostly because you can move into dimensions. One dimension would be the disk spinning, the other dimension would be the head going to the correct lane. And by moving in 2 dimensions, you can actually skip large portion of the data, so you don't need to read all of it. But still, it is slow because you need to spin the disk, and random I/O it is a bit unpredictable because it depends on what's the position of the head at that point and what's the position of the disk at that point. So it was better than tape drive, but still not very good at random reads. And also, but still, the hard drives were best option to run a Postgres database for a quite long time. And at that time, especially before cloud, you would put these hard drives usually next to the physical machine. So at that time, the storage, database storage, was local. But these hard drives had 2 major problems. One is that since there were lots of moving parts, they were prone to failure, so they had a high rate of failures. And the second one, since there is only one head sitting on a platter, the read or write speed wouldn't, like the random read-write speed wouldn't be very good. So to overcome these problems, most database teams, they actually purchased like really big and fancy, like the special hard drives, and they put them into like the fancy RAID configurations to just to overcome these two problems, like them them having lots of failures and also their slow speed. And then what happened is, like as I said, we used to use local storage, but then at one point we switched to remote storage. So what happened? What happened is the cloud happened, basically. So AWS made a bold move and popularized pooling storage remotely across many machines. And basically, they connected big servers with lots of storage drives over a network. And this actually solved both of the two problems I mentioned before, because when you have a specialized storage device, you can, like, for example, replicate the data many times, so that even if one hard drive fails, you would have multiple copies of it, so that the high failure rate wouldn't be a big issue. And also, again, since you have many storage drives, you can also parallelize your reads, so that it would also solve the partially solve the slow random read problem, read and write problem. And just to be clear, the remote storage was already there even before AWS or cloud, but AWS making such a big bet on remote storage made it quite popular. And then the other hyperscalers also followed the suit. And the thing is, at that time, most database engineers or DevOps people thought that, hey, like moving this data at a separate place and adding a network hop would kill the performance. But surprisingly, this architecture worked well enough. So, and then the network attached storage became the default for cloud databases. And I think since like the whole cloud infrastructure started with the remote storage, then rest of the services like Kubernetes, managed PostgreSQL, they all got built on top of this remote storage architecture. And now it requires a conscious effort to move from the remote storage to local storage. And also, for a quite while, the local storage and the local NVMe's, they were too expensive, so they weren't too much incentives to do this move. But I think right now, local NVMe's are getting more affordable. Their failure rate is much, much better than local HDDs. So that kind of brings us to a new architecture that I think we should evolve into. It's based on solid-state disk, like SSDs and NVMe. And contrary to previous architectures or models, the SSDs store the data on flash memory. And each memory cell, you can access each memory cell directly. And this basically means you don't need to spin the disk, or you don't need to walk through the tape. It's like similar to O1 access. So again, like to continue with the previous analogy, I think this is more like array. So you know the position of the data you want to go, and you can just go there at all one time. And both random access is fast, and there are actually multiple lanes in SSD, so you can also parallelize your access, so that gives you even higher performance. And the SSDs were also actually around quite a while, but since they were very expensive, they didn't it wasn't feasible to build an entire architecture based on SSDs. And but now they are more affordable, and over the time they become better in performance. So what happened is the cloud providers that built their remote storage architecture on HDDs, they upgraded that to SSDs. So most of the remote storage we got from cloud providers are now based on SSDs. But it is still stored at a remote location. And also, SSDs were already faster, but then the SSD technology improved even further with NVMe technology, because the traditional SSDs, they used to have SATA interfaces, which were initially designed for the spinning disks. But with the NVMe interfaces, now it's especially designed for the flash disk, it gave another order of magnitude performance improvement to SSDs. So, if I sum up what we discussed so far, is that now local NVMEs are much more affordable, they are reliable, their annual failure rate is maybe 3 order of magnitude less than hard drives. They are fast, but the cloud providers still build their, not just managed Postgres, but all their offerings based on top of remote storage. And I think right now we are at an inflection point. The cloud storage model that's built maybe 15 years ago, it no longer makes sense, especially for today's hardware and today's workloads. For data-intensive workloads and for data-intensive applications like PostgreSQL, I think local SSDs are a better default. That said, remote storage still has some advantages, which I want to mention so that I wouldn't just don't talk about this part at all. The first advantage of the remote storage is that it is elasticity. So basically, you can scale the storage independently from the compute. On the contrary, local storage, it is usually attached. Well, not usually, it's definition, it's attached to the physical machine. So if you want to scale the storage, then you need to either attach more disks, more drives to the machine, or maybe you need to move your workload to a separate physical server. And in the context of PostgreSQL, it is possible to automate this. For example, at ubiCloud, what we do is, if you want to scale up your storage, we create a new standby, we replicate all your data, and once the standby catches up with the primary, we cut over to the new server. So from your application perspective, it is still talking to the same database, but in the background, we scale up its storage or even compute, whatever is necessary. But to be able to have this automation, you need to spend time and effort to build this and test this. And since PostgreSQL and the data, it's very core part of every business, it is something you don't want to make any mistakes. So if you are doing this from scratch, you need to be very careful. Another advantage of the remote storage is durability, because in network-attached storage and those centralized storage systems, they are highly durable because they have a built-in replication. That said, NVMEs are already much more reliable than HDDs. So the concern is less. But still, you need to have some sort of solution, because even if the risk is low, you cannot risk losing your data. But thankfully, Postgres already comes with a pretty good built-in replication mechanism. You can stream walls, you can have a synchronous or asynchronous standby. So building a resilient system with Postgres, on top of local NVMEs, is entirely feasible. But again, if you are managing this yourself, you need to put time and effort and engineering work to do this. And the third benefit of the remote storage is the transparency. Here, what I mean is that you can access and manage the storage independently of the physical hardware. And also, you don't need to know what's going on behind the surface. You just get a remote storage at a size you want, and then like how it is replicated, how it is attached, like what's the network architecture behind it. You don't need to worry about that. It all comes automatically. But with local NVMEs, you need to be more careful about what you are doing. It is like directly attached to your machine. So while doing any operations, like you cannot attach, detach, for example. Like you need to be more, like you need to do everything with more care. But what I want to emphasize is that like all three of these advantages are not advantage for end user. It is advantage for whoever is managing your database. So at a UB Cloud, since like we are building a managed Postgres solution, we are taking the responsibility to negate the advantage of this remote storage, or at least bringing local storage on par with these advantages, and the end user shouldn't have to worry about it. And since, like compared to cloud providers, since they're also like making using database easy is also their responsibility, I think they should also take the burden of making local NVMEs to using local NVMEs as easy as possible. So the gist of what I want to mention is that Postgres, it deserves local NVMe, and come get yours at UB Cloud. And if you have any questions, I would be happy to answer.
Thanks, Burak. Are there any questions?
When you were running performance tests, did you run them all on older Postgres or already on Postgres 18 using async IO and?
I ran them on Postgres 17. I want to rerun them on Postgres 18. The primary reason is the new improvement on async IO. What I expect to see is that the async IO would benefit to Burk workloads, but probably it would benefit more to do remote storage. But even with that, I think like the 8x difference wouldn't disappear. Like it might be, I don't know, maybe 7x or 6x difference. To get an exact number, we need to run benchmarks. I didn't run them at the time I prepared this presentation.
Thanks.
Thank you. Any specific tunings for local storage, like telling Postgres, you know, now you have faster storage, adjust for that?
Yeah, Postgres has few knobs to tune if you want to get most out of the local storage. I think one of them was about the what's the cost of doing random I/O versus a sequential I/O. So for local NVMEs, you can set that to a lower value. There is another one on the number of streams that Postgres process at the same time. I think I/O concurrence or something. I couldn't remember the exact name. So you can tune those. For the benchmarks, I use the same configuration for both remote and local storage to not give extra advantage to the local storage. So I guess if you tune that, the difference would be even higher.
Thanks. I'm not really a hardware person, but there must be some kind of limit on the amount of storage you can kind of attach locally to a CPU, right? Because there's going to be some like hardware bandwidth either on the motherboard or the chip itself. There's going to be a limit. So what's the kind of limit? How much storage can we get per person?
Yeah. There's a physical limit, but that limit is quite high. So like high-end motherboards can have like 16 slots, 16 drive slots, and each of them you can put, I think, there's 30 terabyte NVMe disks that are less common. They are more common 15 terabyte NVMe disks. So I guess if you multiply them, like maybe half petabyte of data you can store. And I guess if you have that much data, then maybe you can have like, there could be even higher models that I am not aware of, and that maybe it could be even more.
Hello, thanks for the great presentation. It's so we see that more and more we are like a lot of efforts are being made to move to local storage. So I want to understand from you that you mentioned one of the advantages of having a NAS is the resilience to failure, right? Like let's say 6 nines of availability. If we want to achieve the same kind of resilience using the local setup, then as you said, you'll have to create replicas, right? And maybe you'll have to make it a sync replica to have like strong consistency and all those things. So did you do any benchmarks on that part, that if you do that kind of apples to apples comparison, then what is the gain that you're seeing?
Yeah, so, well, take a step back. There are multiple ways to achieve resiliency with local NVMe. One is that you can just create an entire standby with its compute and storage. In that case, you need to set up a replication between nodes, and then you could use sync replication or async replication. And another way is you can just mirror the storage bytes. Another one is you can just ship the walls. So like there are many ways, and each would have different performance characteristics. But one point to look at this is that if you have if you want to consider the cost of replication, is that with the remote storage, there is one network hop from compute to remote storage node 1, and then there is another hop to other network storage node, which are close to each other, but still adds another hop. And if you want to have more resilience, maybe you would want to move that to a separate place, and the network would be. So when you consider the cost of replication, both solutions have that additional network hop anyway for the replication. The benefit of the local NVMe is that it don't have the first hop from compute to the first storage node. Also, for one of the architectures that is most common in hyperscalers with remote storage is that the first one I described. So you have full compute node with full with its own storage. In that case, the network hop is like from your application to the database compute, from database compute to database storage, then from other standby compute and standby compute to standby storage, and then each of them also get replicated multiple ways. So like it adds lots of hops, and like all of them adds extra penalty.
Thank you. Great talk. I will add a bit on the previous question because it was very similar to mine. So I'll phrase it in two ways. First of all, in 2025, I think the default should be local NVMEs, but from a, let's say, business perspective or go-to-market approach in a product, how often do you see this approach in larger businesses, right? Like how high is the adoption for this approach in terms of deployment at the real production scale? I don't know, 20 plus terabytes of data. And I would like to add one more thing, which I consider is very awesome, is the fact that you even have bandwidth in terms of network limitations, right? We encountered this a lot with our EC2 hosted Postgres's with pretty high IO2 type EBS. And you can configure EBS, yeah, a lot of IOPS or throughput, whatever, but then your EC2 limitations hit, and that's not quite as transparent. So my overall question is, let's say we want to move to local SSDs, but even from a business perspective, the adoption rate in 2025 isn't as high, and usually when you're digging into this, most of the businesses go with this approach primarily due to cost considerations, which are pretty legit, but at the same time want resilience for your product, right? So as an engineer, I'm thinking first about resilience, then finance is thinking about cost, and it's a balance, right?
Yeah.
So.
Yeah, I definitely agree. So you had multiple questions. I'll answer the ones that I remember, and then you can add the ones if I forgot. You asked, like, what's the adoption rate? If I ask this question, I don't know, 2-3 years ago, I would say the adoption was quite low. But now I see an like uptick, like exponential growth, like adoption. It's still much less than where I should be, in my opinion, because as you said, like it's a new, well, not new, but it's a new comparatively new architecture that people have concerns, and there aren't many options as well. So I think Avon had local NVMe managed PostgreSQL, ubiCloud has, and they recently PlanScale introduced. So, so there are 3 providers that gives this service, and all the hyperscalers, they don't, and majority of the people, they either run it on-prem or one of the hyperscalers. But I guess as time passed, the adoption would increase. And this is one of my goals with all this talk. And you also talked about cost and the resiliency. The cost part is actually interesting. Like, even if you just look at EC2, and an instance with remote storage, and if you compare the price of that with a same spec instance with local NVMe, but the same amount of local NVMe plus same amount of EBS, the one with the local NVMe is actually cheaper. The reason is that when you have 100 gigs of EBS volume, it actually uses more in the backend because it has own replication. So the cost becomes an important factor when you want to add the second node, because you want the resiliency. The thing is, if you want to have resiliency, you would want to have HA setup for remote storage solution anyway. So if you are going to double or triple your cost there, then you can double and triple your cost with the local NVMe as well. And at the end, the final price would be slightly lower for local NVMe. So you would get same resilience, maybe. Like, we need to check the exact numbers. Like, I don't know. I guess EBS replicates 5 times, if I remember correctly. So if you have 2 copies, then you would replicate 3 times, so you wouldn't have the same. But NVMEs are already quite stable, so like maybe 3-way replication or even 2-way replication is fine for most use cases. And the cost is, well, same or maybe even cheaper.
Any other questions? Yeah.
This is just like, there's another question I don't really know anything about myself, but I'm with NVMEs, right? There's kind of quite like it's quite large, but there's an upper bound the number of like read-write operations you can do on an NVMe before it will sort of stop being as reliable. I'm just wondering, maybe it's more of a question about like how you guys specifically do it, but if you've got like a machine with 4 or 5 NVMEs attached, you know, I guess, if one of those gets close to the limit of breaking, do you then have to rotate the whole machine, or is there like to a different machine entirely, or can you like hot swap out the NVMEs whilst it's running to sort of, I guess that would make it easier, I imagine?
Actually, this is a bit of how we approach building managed services. So everyone's take would be different. But what we built at ubiCloud is, so for example, when you want to scale the compute, you need to do a failover to another machine. When you want to scale the storage, you need to failover to another machine. When you want to upgrade, you can do in-place upgrades, but it is risky. So if something goes wrong, you would want to fall back. To prevent that, what we do is we create a standby, upgrade that, and failover to that. So we built the architecture based on doing an entire copy and cutover. So in that architecture, the benefit is, since you don't do anything in place, then if something goes wrong, it doesn't affect the customer, so the uptime is high. And also, you can limit the downtime to a cutover time. So there's no downtime until the new server caught up. Since it's a planet, so you can just update the, DNS record and like shut down, like fence the other server. So because of all those benefits, we built the entire architecture based on this create a new one and swap mechanism. So in our case, when one of the NVMEs are close to its end of life, what we would do is we would swap the entire system, and then the other machine, now it's empty. There's no workload running it. Then we would do any maintenance we want to do on it. But this is our take. But personally, I like this approach because it gives you a very predictable outcome without risking any downtime to end user.
Also a question from someone who has a lot to learn about hardware. Do you mind going to the slide with the picture of the NVMe and actually explain in the picture how the random access would work here?
Okay, I also don't know every detail, but my understanding is these are data lanes. And at these components, these are the data cells. So when you get a request, it knows on which data cell that particular data is stored. And inside of each data cell, there are also parallel lanes. So like even in one data cell, you can have multiple reads or write operation going on at the same time. But I also don't know the internals of this very much, so take my word with caution.
Any other questions? We still have some time for more questions. Yeah.
I'll just follow back on the default 2025 approach, which is the cloud NVMe stuff. When you think about high availability, I'm not sure if ubiCloud offers this, but if you have a multiple availability zone setup, even with on-prem or local SSDs, is that a consideration? Like, do people run it this way or no, stuff like that? Like you have multiple attached SSD to your products, but then you run it in multiple data centers, or pretty much have the high availability in terms of the region itself or the zone itself. It's something to consider. And if so, that's fine, but taking just into consideration the cost, right now you pay for data transfer as well, right? You pay for everything when you do high availability in the same availability zone in terms of EC2 going in and out.
It depends on provider. So at ubiCloud, we have our own data centers. So like we don't pay like EC2 data transfers. But the ubiCloud is designed to be able to deploy it anywhere. So it's like the big software stack that is partially, like mostly agnostic to the underlying hardware. So we have ability to deploy AWS data centers as well. And in fact, we have a few customers that have their application on AWS and they want their database on AWS, but with the NVMe. So for them, we deploy ubiCloud to AWS data centers. In those cases, if you are in the same AZ, you don't pay any network fees. But if you want to go across AZ, even if in the same region, then you would have to pay network cost.
Anyone else? Well, if not, then let's thank Burak again. There will be a coffee break now, and then we'll continue.
Yeah, thanks, everyone. We also have a booth at just the entrance of the main hall. If you have any questions or if you want to hear more about what we do, or local NVMEs or managed Postgres, everyone is welcome.